Si vede? Gli mortacci. Allora, dovrebbe essere ripartito un attimo su YouTube, se lo vedi. Lo vedi?
Vediamo. Sì,
Ci sono le slide?
sì.
Ok,
Dovrebbe essere partito un attimo su YouTube, se lo vedi.
Mhm.
perfetto. Mamma che fatica. Okay, good afternoon, everybody, or good morning if you are on the other side of the ocean. Sorry for this small delay due to some minor technical issue here with the streaming. So anyway, welcome everybody to the latest seminar in the Machine Learning for Science series. So this afternoon we're going to have Michele Ceriotti from EPFL in Lausanne in Switzerland. So Michele is one of the pioneers really of using various machine learning methods for, in particular for material science. And today is going to discuss some of the of such methods applied to chemistry and various property. So for those of you who don't know Michele, so he graduated from Milan University, and then he did his PhD in the group of Michele Parinello at ETH. And after the postdoc time, he took up a position at EPFL in Switzerland. So as usual, please use the box to post questions, and the questions will be then read at the very end. And as I said, usually as you have questions as we go by, please post them so we'll be kept there for later on. Okay, without any further ado, please, Michele.
Thank you very much, Stefano, and thank everybody for joining in these difficult times. Indeed, I'm not from EPFL, but I'm from my living room. And I'm going to give you kind of a comprehensive overview of what has been going on in my group over the past couple of years connected to machine learning for materials and materials discovery. Given that, as I mentioned in the abstract of this talk, I do feel that there is a little bit of excessive hype around machine learning. I decided to always start these kind of presentations by trying and motivate why I started caring about machine learning and why I think that after all, even beyond the hype, it's a very good idea to use some machine learning in science in general and in materials modeling in particular. So the general idea, at least of the way I see materials modeling, being someone who is interested in modeling of materials at the atomic scale, is the idea is really to extract some direct insights into the structural property relations that determine the behavior of materials in the end at the macroscopic scale. When you want to build something, you want to choose your material and decide how to process it. But all the multi-scale modeling that allows you to make a prediction on how a certain material will behave when you build the wing of a plane eventually rests on properties that can be computed at the microscopic scale. So in order to evaluate these microscopic quantities, you have to start somewhere. And if you decide to start from first principles, you're going to start by taking a precise geometry of your system. So you take a certain configuration of the nuclei, and you will probably find some approximate method to solve the Schrödinger equation and determine the energy, polarizability, or whatever property that might be interesting then to be translated into a macroscopic property that is important to solve some kind of applied problem. Now, if, like I do, you actually care about the properties of real materials and real molecules, well, real materials and real molecules are not just one static configuration. They will undergo fluctuations driven by temperature or by the quantum mechanical nature of the nuclei. And then the macroscopic properties that you really want to obtain are not the result of a single configuration of the nuclei Q, but are an average, an integral over a certain probability distribution. And here I'm writing the classical case where you have a Boltzmann distribution and you need to average over all the possible configurations of the nuclei weighted by the Boltzmann factor. So in examples of scenarios in which you might want to compute integrals of this kind involve, for instance, computing free energies, and actually this also applies to hard materials. So here you have an example of the free energy of a hydrogen atom in iron, and even for something like this, you do need to take into account the fluctuations of the nuclei, including also the quantum mechanical fluctuations of the proton. Same if you want to study water. Well, one thing that I used to say is that if you try to compute the pH of water and you treat the nuclei as classical particles, the pH of water would be 8.5. So if you want to get a water with a pH of 7, it's not enough to have a very accurate electronic structure method, but you also need to treat the quantum mechanical nature of the nuclei. And then if you want to study something like a phase transition, more often than not, you will have to study a activated event that is connected to the nucleation process. So every time you want to tackle problems of this kind, you don't need to compute properties of a single configuration of your system, but you need to compute properties over and over again, typically hundreds of thousands or millions of times. So the problem is that when you want to do this, you really need to find a compromise between the accuracy of the energetics that you need to compute. And many of you might have seen this concept of a Jacob's ladder, in which you go from an empirical model to DFT to some post-Hartree-Fock methods and to full CI. But if you're interested in properties of materials at finite temperature, having very accurate energetics is not enough, and you also need to have an accurate sampling of the appropriate ensemble. So, you could start from a static approximation in which you compute the a single configuration of your system. You could use a harmonic approximation, use some kind of perturbative form, or go all the way to performing molecular dynamics and sampling. So the problem is really that you need to find the balance between the accuracy of the energetics and the accuracy of sampling, because if you go along this axis, you will have to compute energy, forces, and properties many times. And this is where I really feel that machine learning, even just into its interpolative behavior, can be extremely helpful, because more often than not, when you're performing thermal or quantum sampling, you will be computing the properties of structures that are quite similar to each other. And so this is where machine learning can help you achieve the accuracy of first principle calculations, using, however, just a small number of reference calculations, and then using a model to approximate these predictions and be able to compute them millions of times and compute really finite temperature properties. So how do you build a machine learning model that is efficient, so that that allows you to learn, to train your prediction based on a small number of reference calculations? So I maintain, and I mean I'm not alone in maintaining these, that the two ingredients that allow you to achieve efficient machine learning of atomistic properties are symmetry and locality. So what is symmetry about? Well, symmetry is about making sure that when you make a prediction, it will not depend on trivial symmetries of your system. So the point is that your machine learning algorithm is a stupid thing, and if you just provide as input the coordinates of your atoms, the input of your model will depend on the absolute position of your molecule in space, the way you label the atoms, or how the molecule is oriented. So in order to achieve something effective, you need to build a representation of your system in which the Cartesian coordinates are converted in a form that fulfills all of these physical symmetries. So here I'm going to give you an introduction, a very brief overview of a formalism that with a couple of very good students I developed last year that tries to build a mapping between Cartesian coordinates and an abstract ket. I'm using Dirac notation here for those of you who are familiar with the use of Dirac notation in quantum mechanics, that represents your structure in a symmetrized fashion. So the idea is that, let's say that you want to describe a substituted graphene sheet, your input configurations will be the coordinates of all of your atoms and the nature of the atoms sitting at each position. However, as I mentioned already, a representation like this would not fulfill the most basic physical symmetries. So we start by representing instead the system as a decorated atom density. So the idea is that now the system is represented as a ket, and in a position representation you can write this ket as a sum over the atoms of a Gaussian centered on each atom. And then each Gaussian is decorated with an abstract vector. You could regard this a little bit like a spin component or as a color that indicates whether the density that you have in a certain point is associated with a carbon, nitrogen, or boron. Now, this representation is invariant to permutations. So if I swap the coordinates of two atoms of the same kind, the density remains the same. However, if I rigidly shift this system, this will become a different function of R. So this representation is not translationally invariant. So what you can do is build a hierarchy of representations that are symmetrized versions of this density. And in particular, you evaluate the density in 2, 3, 4 points, and then you average over all the possible absolute translations of this density. And if you do this, two things happen. Well, first of all, your representation becomes translationally invariant. And second, your representation naturally splits into a sum of atom-centered contributions. So basically now, rather than representing my structure as a density fixed in an absolute position of space, I am representing my structure as a sum over all the atoms of a density that is centered on each atom. Now, since the density is atom-centered, you see here in the expression for the density centered on atom J, only distance vectors enter, which means that now this representation is translationally invariant. It is not, however, rotationally invariant because it depends on the absolute orientation in space of Rij. So if to make this atom-centered description invariant to rotations, you need to integrate one more time and average over rotations. And what I really, really like is that these invariants are very directly related to correlation functions. So if you integrate this object over rotations, you end up with something which is equivalent to pair correlation functions. And if you integrate over rotation the product of two of these atom-centered densities, you end up with something which is formally equivalent to a three-body correlation function. And you can go on and build higher and higher body order invariants. And I find very pleasing that the building blocks of a machine learning model are now the same body order correlation functions that enter, for instance, the statistical mechanical theory of liquids. A very interesting side effect of representing these structures in terms of an n-point correlation function is that if you build a linear model out of these descriptors, the weights in this linear model are effectively just n-body potentials. So if you use a two-body correlation function as your descriptor and you build a linear model, the weights will be a pair potential. If you build a use a three-body description and you use a linear model, your weights will be a three-body potential. So there is really a one-to-one mapping between the body order expansion and these body order representations of a structure that incorporate all of the physical symmetries. And a very nice side effect of this construction, and the reason why I'm using this Dirac notation to introduce these different body order terms, is that depending on your choice of basis functions, you can recover many of the features that have been used very successfully over the past 10 years to build machine learning models. So essentially this construction builds a link between different kinds of representations. So for instance, if you project this body order density onto, you get two-body Beller-Parinello. If you use the three-body description, you will get three-body Beller-Parinello. So in the end, that the basis function that I like to use most of the time is a basis function of radial functions and spherical harmonics, because they are a very natural way of incorporating rotational symmetries while giving you a complete basis. And if you do this, you soon realize that actually this three-body representation, once written on a basis of radial functions and spherical harmonics, is exactly identical to the construction that you obtain in the SOAP framework of Gabor Chani, Albert Bartok, and Rishi Kondor. So effectively, most of the applications you will see in this presentation are based on an implementation of SOAP. But I like to regard these as just one possible choice out of many to represent n-body correlation functions. And you can really show how this is fully true densities. Now there is a subtle aspect that we've been trying to come to terms with, which is the fact that you need to choose where you stop this body order expansion. Now, if you want to use a linear model, then truncating the body order expansion is equivalent to truncating a body order expansion of the potential. However, many people use nonlinear kernels or neural networks, which mean that your model is a nonlinear function of this set of features. So if your set of features was a univocal mapping of a structure, then you would have a guarantee that a sufficiently complex nonlinear function would be able to represent any function. It turns out that actually these atom-centered representations are not univocal, and you can build counterexamples that in which you have two environments that are clearly different, but have exactly the same two and three body representation. And you can also build counterexamples for higher body order representations, and you can check out this preprint in which we are discussing, in which sense this is a problem and in which sense this is not such a big problem, because in the end there are aspects that still allow you to learn even with this fundamental shortcoming of a truncated body order expansion. Just to conclude my discussion about symmetries, I just want to stress that even though the potential energy is perhaps the single most important property that you want to predict, because it describes which states are accessible to your system, there are many other properties that you might want to compute: dipole moments, polarizabilities, and these properties are not necessarily scalar. So if you want to learn something which is like a vector, like a dipole moment, for instance, you don't want it to be invariant to rotations, but you want it to be covariant to rotation. So you want that when you rigidly rotate a molecule, your prediction rotates in exactly the same way. And it turns out that within the same formalism that I was discussing before, using this Dirac notation, you can build an appropriate basis to represent covariant functions such as vectors and tensors, and I will give you some examples of what you can do with these tensorial machine learning models. How about locality, which I mentioned before, is the other ingredient that is crucial for an effective machine learning model. So the point is that in the end, you want to predict a property that is a property of your entire system. If you compute the energy of your system by an electronic structure method, there is no single way of decomposing that energy in atom-centered contributions. The energy is a global property of your system. However, if you use an additive model, such as those that arise very naturally when you build these symmetrized representations, you automatically assume that the property that you're trying to learn, the total energy, for instance, is a sum of atom-centered contributions. So in a certain sense, an atom-centered decomposition is a very natural outcome of imposing a translational symmetry. And then you can hope, so an advantage that you have by imposing some kind of locality is that now you can hope to be able to learn based on relatively small and simple systems, very much like, the small children version of Lego bricks. And once you have learned from these how you can put different shapes together, you can use this knowledge to build and make predictions for something which is much more complex and potentially much more interesting. Now, the crucial question here is how local is local, and I will return on this later. But at the moment, you can ask yourself very pragmatically, how short-sighted am I? Can I just take a cutoff radius of 1 angstrom, 2 angstrom, 12 angstrom? How far do we need to go? So in the spirit of being data-driven and machine learning, you can try and let your data answer this question for you. And what you can try and do is build a machine learning model. In this case, for instance, I'm trying to learn molecular energetics, and you build learning curves, and this is essentially how accurate is my model in making a new prediction after it has been trained on 500, 1,000, 2,000 structures. So something which is perhaps not completely obvious is that initially, if you use a very short range cutoff of just 2 angstrom, your model performs best. And this is because I'm looking at cohesive energy of molecules. And within 2 angstrom, I can describe the covalent bond. And the covalent bond contributes a great deal to molecular cohesion. And therefore, just short range information is enough to learn a great deal. And if I have a small number of training structures, I'm better don't get distracted by what's happening in the far field. However, if you have more data and you try to learn the short-range model, you see that the learning curve saturates, and this is because you can't learn hydrogen bonding, for instance, because you can't describe the hydrogen bond with a 2 angstrom cutoff. And so the idea is that then you can go to 2.5, 3, 3.5 angstrom, and the more data you have, the better you can learn for longer and longer range information. And the idea that we had is that actually you can try and put the multi-scaledness of interactions back into your model by building a kernel, if you are using a kernel method, or features, if you are using a feature-based learning scheme, that weights information coming from different distances in a way that reflects the importance of a certain length scale on the actual property. And if you do that, you can get a multi-scale model that predicts better than any of the individual models. And in the end, for this QM9 data set, gets an accuracy of 0.14 kilocalorie per mole, which is ridiculous because it's way lower than the intrinsic accuracy of the reference method. Another example in which you can extract some insight into the way your machine learning model recovers chemical information, you can obtain by looking at how you represent different chemical species. So I told you that in this formalism, you can regard the different atoms as a decoration, as an abstract vector that decorates this spatial density. And the point is that when you implement this in practice, what you do is effectively like saying that all these vectors are orthogonal to each other. But you can also use a basis that is smaller than the total number of elements that you have. And then what you're doing is kind of going back to a classical elements picture in which there is a small number of chemical archetypes, fire, stone, water, and then your actual chemical elements are just a linear combination of these chemical archetypes. And actually, this reduction in dimensionality of the chemical space can be extremely useful, again, when you have a limited amount of information. Here, this is trying to learn the cohesive energy of El Paso lights, which is a data set, and this contains, the structure is always the same, but you have a different combination of 40 chemical elements. And if you use a SOAP descriptor in which all the 40 elements are orthogonal to each other, you can learn, but you learn rather slowly. If you reduce the dimensionality of chemical space to 1, that's not complex enough to learn the behavior of the periodic table. But now, if you reduce it to 2 or to 4, you get enough flexibility, and at the same time, you are compressing a 40-dimensional space down to 2 or 4 dimensions, which allows you to learn much, much faster, because you can learn from oxygen the behavior of sulfur, for instance. And as a byproduct of this, which I find kind of neat, if you restrict the dimensionality of the chemical space to 2D, each element is a point in 2D. And so you can plot out the elements as a map in 2 dimensions, and you see that just from a data-driven construction, elements that belong to the same group in the periodic table get projected together. And a little detail that I really like is that, it's not always true. So hydrogen, that doesn't really belong with the alkali metals, doesn't get projected with the alkali metals, but it gets projected together with the chalcogenides. So in a certain sense, the data tells you that hydrogen is not really your average alkali metal. So this gives you kind of an introduction of the mathematical foundations of all of the machine learning work that we have been doing, but I also want to give you a few examples of what you can do with this, because in the end, I want to stress at a certain point, I want to stop making fancy plots and fancy maths, but I want to solve with machine learning, real chemical and material science problems. So for instance, you can ask yourself a very difficult question, which is about the stability of different phases of water. And in particular, you might know from the fact that snowflakes are hexagonal, that the stable phase of ice has hexagonal symmetry. However, there is also a cubic phase of ice, which is very difficult to synthesize, but every experimental measurement and every computational study predicts that the free energy of the cubic phase should be very, very close to the free energy of the hexagonal phase. The problem is that the two free energies are so close that in order to be able to compute that to a sufficient level of accuracy, you need at least hybrid DFT reference calculations, as well as full thermodynamic sampling of proton disorder, classical and quantum fluctuations of the nuclei. Doing these thermodynamic integration and averaging over different proton disorder states by first principles is completely impossible. So what we do here is using machine learning as a stepping stone to perform all of these time-consuming thermodynamic integrations. And then, since machine learning is accurate, but it's not accurate enough to predict the relative free energy of cubic and hexagonal ice, we do free energy perturbation to promote machine learning to full ab initio accuracy. And in this way, we can do just a couple of thousand single point ab initio calculations rather than several million. And when we do all of these, we can predict with absolutely no fitting parameters the melting point of water within a few Kelvin. And we can predict that hexagonal ice is more stable than the cubic one. And what is interesting is that we find that the quantum mechanical nature of the hydrogen atoms is crucial to tip the balance in favor of the hexagonal phase. Otherwise, the cubic phase would be the most stable. So you might say, okay, water is a simple system, but you can also do more complicated systems. You can do molecular materials, and you can, for instance, predict the relative stability of different polymorphs of, in this case, pentacene. And the reason why I like this slide is that the substituted pentacenes have very different learning efficiency using the very same machine learning scheme. And the reason why is that this 5B structure is non-symmetric, and so the crystal structure landscape is much more complex and much higher dimensional than the crystal structure landscape of non-substituted pentacene, which is why you need more training structures to approach the same level of accuracy. Another aspect that I want to stress is that you might also want to be able to study properties that are not just the potential energy. And here I have a nice example, which is the prediction of the NMR chemical shieldings in the solid state. And this is something that we are actually doing in collaboration with the experimental group of Professor Emsley here at EPFL. Well, I should say there at EPFL. They are very interested in being able to predict chemical shieldings in the condensed phase, because the only way you can do NMR crystallography is by comparing experiment and theoretical predictions of different phases to find the one that matches most closely the experiment. And the problem is that doing GPO-DFT calculations of the chemical shieldings is very time consuming. So we built a machine learning model that we called ShiftML, and that you can actually try for yourself. Just go on shiftml.org, you're already in front of a computer, and you can essentially load a XYZ file with your crystal structure, and you will predict the chemical shieldings of the different atoms that are in it. So in these times of everybody ambulance chasing for coronavirus science, the closest you will get in this presentation is this example where we can use machine learning to predict the activity of a drug molecule against a protein. And here the idea is to get a set of decoys and a set of molecules that are known to be active and a set of molecules that are known not to bind to a certain protein. And then using just a small number of training structures, being able to predict all the others. And what you can see here is that these curves should be following this edge for a perfect classifier and follow the diagonal for a classifier which is as good as random. And interesting aspect in this example is that for most of the molecules we perform fantastically. If we play all the tricks of the game with fewer than 50 training structures, we can predict with 99% accuracy whether a new molecule will be active or not, except for this protein. And it turns out that the reason why this protein doesn't work is that the data set that we used, we don't and didn't know anything about biophysics, so we just downloaded an existing database, and the database contained a clerical error so that the same molecule for this protein was listed both as binding and as not binding, which was confusing the classifier and leading to very poor performance. So we went back to a previous version of the same dataset that didn't have this clerical error, and FGFR1 goes back in line with all the other curves. I was mentioning tensorial predictions, and we can use these to predict, for instance, molecular polarizability. So molecular polarizability is a tensor, it's not a scalar, And in order to predict it properly, you need something that can predict tensors. And this works very, very well. We get an out-of-sample error, which is half. So we are training on couple cluster accuracy references on very small molecules, but still we can outperform DFT on making predictions on the largest molecules we could afford to run couple clusters with. And you can try also this by yourself on alphaml.org. When I should stress that, I am not a quantum chemist, and we could only get the fantastically accurate reference calculations thanks to Rob Distasio and his team. Now, another application of tensorial machine learning involves learning the charge density, so the three-dimensional charge density on a molecule. And the idea here is that we learn a little bit like a resolution of the identity, and actually the accuracy improved massively when we started using a resolution of the identity basis. So we learn the density expanded as a sum of atomic functions. So the coefficients in this expansion will transform like spherical harmonics, which means that we need to make an expansion. Basically, we need a machine learning model that can describe tensorial properties. And if you do this, you can train only on small organic dimers and still be able to make predictions for the charge density of large protein molecules. And since Clémence Cormier-Boeuf and her team have been able to apply this to ubiquitin, which is a small but reasonably sized molecule. And once you get the density, the interest in this is that you can use the density, for instance, to compute the electrostatic potential and a lot of other observables that depend directly on the density. Now, speaking of electrostatic potential, I want to stress what I believe to be one of the most clear shortcomings of current machine learning schemes. And this has to do with long-range interactions. Now, if you needed to explain to your grandmother why long-range interactions are tricky, I typically use this night sky paradox, where the idea is that light intensity decays as 1 over r square. But now imagine that you were to integrate the light intensity coming from stars that are at distance r. The volume element for the integral in spherical coordinates increases as r square. So each shell in the integration over r that will give us the total intensity that reaches us, night sky should be bright. And the fact that it's not, it's proof of the fact that the universe is not static, infinite, and uniform. Now, the same argument applies also to electrostatic interactions, only that it's even worse because electrostatic interactions decay as 1 over r. And actually, if you studied, this is really undergraduate solid state chemistry, if you compute the cohesive energy of an ionic crystal, you have to be careful because the infinite sum of the electrostatic potential that gives you the cohesive energy is conditionally converging, meaning that depending on the order of summation, you get a different answer. So if you sum over growing spheres or over growing cubes, you get a different limit for the cohesive energy. Now, how are we going to learn something which is so intrinsically long-ranged without giving up the locality of machine learning that gives us this Lego brick transferability? The idea that we had is basically, okay, what I was forgetting, I mean, if you try to learn something which is intrinsically long-ranged, like the cohesive energy of a charged molecular dimer, so this is the DFT result, you make a prediction in the local model. Unsurprisingly, as soon as the two molecules are further apart than the cutoff distance, the energy doesn't change anymore, and you get a crappy prediction. So you might say, okay, I can increase the cutoff distance, but we know, based on the plot I showed you before, that increasing the cutoff distance makes machine learning less efficient because the building blocks become more and more complex. So the idea that we had was to use building blocks that are still local, but reflect long-range correlations with the correct asymptotic behavior. So the idea is that we start from this decorated atom density that we use as the foundation for the local machine learning model, and we compute, in the case of the electrostatic potential, just by solving the Poisson equation, the potential that is associated with that density. And then we symmetrize the potential rather than the density. And this leads to a local decomposition of this fictitious potential. This is not an actual real potential. This is the fictitious potential associated with the atom density. And we use this expansion of the potential as a basis to learn our properties. And if you do this, you get a prediction that even though it's trained only on short-range interactions, it can extrapolate quite accurately, depending on the dimer, to the full dissociation limit of the two molecules. So I just want to very, very briefly mention two technical aspects, which I think are very important, because, in the end, you want to make a machine learning model, but you also want to know how accurate is your model. And I just want to make a second of advertisement for, we have this approach which is very similar to what many people are doing, involving essentially making multiple predictions, building multiple models and making an ensemble of predictions. But we have a couple of tricks, one based on the fact that we're doing kernel regression. We built the model in such a way that predicting the n different models is completely inexpensive. So you get multiple predictions at the cost of one. And then how do you estimate uncertainty based on these multiple models? Typically by computing the standard deviation of the predictions. And this is usually a qualitatively good predictor, but it's not quantitatively right. And the idea that we had was to use a calibration procedure to make this qualitative estimate actually quantitatively very accurate. And another trick that we use is to recalibrate the predictions so that we can do uncertainty propagation very naturally. And here I just wanted to give you an example. Here we are doing tensorial prediction of the polarizability to then compute a Raman spectrum. And what we do is we do multiple predictions of the polarizability. So we have a committee of models that at each point in time computes a different polarizability. We use the different series to compute multiple spectra. And this gives us a way of computing the uncertainty in the end result, which is a Raman spectrum. So we can compute a machine learning estimate of the Raman spectrum with full uncertainty quantification. Another soap in kernel regression, because you have a systematically converging basis. So this is just a matter of computational efficiency. But if you're using something like a better Parinello framework, when you want to have perhaps 100 symmetry functions as the input of your neural network, you want to choose wisely these symmetry functions. And we do this, you can do this, essentially you have many different methods that allow you to reduce the number of features that you use with very little loss in the accuracy of your model. And as a concluding considerations, I focused most of this talk on supervised learning, meaning that I was really building a model for a property or a material. However, very, very often, you also want to understand something more intuitive about, for instance, you have computed a high throughput set of carbon allotropes, and you want to understand something about these. And one thing that you can do is build maps that reflect structure property relations and that, for instance, give you clustering of groups of structures that have very similar properties. So you can understand, for instance, you can't see this because this is not interactive. If you want the interactive version, you can go to chemiscope.org. But all of these islands corresponds, for instance, to layered allotropes of carbon. This island corresponds to diamond and Lonsdale-Light. All of these are different disordered carbon structures. Now, how can you build these maps? Well, a simple way would be to use principal component analysis of the kernelized version of it. We actually have found a very nice method from the 90s, which is a linear method, so it's very simple, no autoencoder deep stuff, which adds a lot of complexity and gives you a map that depends on the phase of the moon. This is a linear, very simple prediction. And what is nice is it allows you to combine a prediction that is based on a principal component like loss. So you try to have a low-dimensional description that preserves the variability in your data set, but also you try to make sure that this latent space is also good to make a prediction of your end properties. And effectively what this means is that you have a mixing parameter that allows you to go from PCA, where you have a prediction that is very representative but is very bad at predicting properties, and linear regression that gives you a good prediction of the properties but very poor representation of the variability of your dataset. And we have extended these to use a kernelized scheme, which allows you to get a much better accuracy in the structural property representation. I think, I still have 2 minutes on my clock here. So I just want to give you another example of how you can combine supervised and unsupervised learning. So those of you who are material scientists have certainly heard of the convex hull construction. So in general, this is an idea whereby, for instance, you predict many phases of a binary system that are metastable, and if you then try to synthesize this material at a given composition, if you are trying to synthesize this phase and you just have the composition fixed, this phase will decompose into these 2 phases because the free energy of physical mixture of the 2 phases has the same composition but a lower free energy. So the idea that we had was to generalize this construction, and rather than using the composition or the density as the axis of the convex hull, we use kernel principal component directions, which are good then to couple to different possible thermodynamic fields. And for instance, if you apply this to a I've been initial random structure search of the phase diagram of water, and this is a work in collaboration with Chris Picard and Czernitz, as well as my collaborator Edgar Engel and Andrea Anelli. Not only you get out of the 100,000 structures that were coming out of the random structure search, you find all of the 17 known phases of ice, and 17 phases that might be stabilizable somehow. And to give you an example, we get a couple of structures that are known clathrates. So this is a pure water phase, so this is just a cage, but this is the cage that using a templating agent, methane or some other small molecule, as a perturbation can be made locally stable and therefore synthesizable. So to wrap up this bird's view overview of our machine learning activities, I want to thank all the members of my group, thank the funding bodies that supported this research, and leave you as a take-home message the idea that machine learning, even though it's certainly overhyped, it's also a very useful tool for a material scientist or a chemist, particularly, I think, if you're interested in doing statistical mechanics and studying systems at finite temperature. Because everyone who has been doing ab initio molecular dynamics has been wasting a lot of CPU time computing almost the same structure over and over again. And machine learning basically allows you to avoid computing the same structure over and over again by giving you a cheap to compute model that interpolates between a small number of ab initio calculations. And now if you want to reduce to the minimum the number of ab initio calculations that you want to do, you might want to build a machine learning model that is effective, and to achieve that, incorporating symmetry, locality, and some kind of locality preserving representation of long-range physics is very, very important. So if you want to download these slides, you can find them at this URL. And I guess that what I'm going to do now is switch to the YouTube page and look at the questions that you have given me.
Thanks a lot, Michele. And I guess, so this seminar unfortunately cannot end with people clapping their hand, but there is a virtual clapping, I guess.
Thank you. Virtual, thank you.
So we give a few seconds, since there is a little bit of a delay in the questions. So maybe, I have a couple of questions that actually arrive on my mobile phone, so I can ask this first maybe. So one question is from Alessandro Lunghi, who is a research fellow in my own group, and essentially is asking whether in general this machine learning based kernel method that look at essentially energy property, whether they can be used for molecular dynamics, and how efficient are to use in molecular dynamics.
Okay, so I just wanted to say that I was just a child bomb, and my son brought me a saw. But anyway, so how this can be used in molecular dynamics? Well, all of these can be very, very easily modified to predict forces and to learn from forces. It's actually, people have been doing force matching for 50 years, and it's exactly the same thing. So your model predicts the energy, but it's a function of atomic coordinates. So if you pick your representation right, it's a smooth function of the atomic coordinates, so you can derive your model, and then you can predict forces and you can train from forces. So there is no problem in using any of these models with molecular dynamics. And actually, using these models with molecular dynamics allows you to do a lot of smart tricks. So for instance, something that we have been doing, so I'm kind of a pragmatist. So if you want to study a really complicated system, for instance, we are studying some homogeneous catalysis where we have acid and hydrogen peroxide in a phenol solution. It's very hard to collect enough reference calculations to be able to build a machine learning model that is stable. So what we are doing is using the FTP as a baseline. And the point is that the FTP is kind of expensive. It's cheaper than the FT, but it's still much more expensive than the machine learning model. And so you can do multiple time stepping. So I actually think that machine learning is beautifully suited to molecular dynamics. You can really combine a lot of the tricks of the trade of molecular dynamics with these machine learning schemes, and it brings you very, very far.
I guess, Michele, there was kind of a second side of this question, and the question is, but since it's a machine learning, what happens if you find that your molecular dynamics simulation bring you to configurations that are really not known by your machine learning method?
Yes, absolutely. And this is the reason why, even if very rapidly, I wanted to show these couple of slides that were about uncertainty quantification. It's very important. I am really pushing all of my students and collaborators to, every time we write a machine learning paper, to also compute uncertainty estimations. And then if you manage to make the uncertainty estimation cheap, as you can with this kernel version of it, you can run it. Basically, you always run the uncertainty quantification as you run MD, and every time your prediction is more than 3 sigma outside of your confidence region, you know that you're in trouble and you need to update your machine learning model. So you can very easily incorporate an active learning component to this.
Okay, thanks a lot. Maybe another question actually from myself. Is there any particular method representation that actually perform better to, I mean, in the sense of efficiency, to establish distances between configuration. So in other words, I mean, you have two molecules. Can you say whether these are very similar or very different in a way which is quick to calculate, I guess?
So, okay, so there are two questions here. One, a way that can distinguish configurations, and the second, that is quick to calculate. So, I would have thought that something like SOAP or equivalent to SOAP would have been a good way of telling two configurations apart, because empirically, myself and also Gabor Chani and pretty much everyone with whom I had a deep discussion on this issue was convinced that SOAP was a unequivocal mapping of an environment. So if two environments have different SOAP, so we thought the environments are different, and this is relatively cheap to compute. And this was until I gave a presentation in Moscow, and a student came to me after the talk and told me, what you say is just wrong. I have a counterexample. And that started basically this work on trying to understand this counterexample. So in practice, my current understanding is that if you want to have a guarantee to have an equivocal representation, you have to go up in body order, which is expensive. However, in practice, it's relatively unlikely for you to find two structures that are different but have the same SOAP features. So something like SOAP might be a good way of telling two structures apart.
Okay, let's see. I don't see any more questions, so maybe I'll maybe ask a last question, and if no other are coming, I think we can maybe stop here, I guess.
Yeah.
I just wondered actually. So, of course, one thing that sometimes disorient kind of material scientists or electronic structural people that come from kind of a culture where you can construct systematic approximation to whatever you're doing and more or less you know where you're going, is that in machine learning you have a lot of representation, a lot of machine learning methods and so on. Do you think there is a systematic way to navigate that? So in other words, is there a systematic way to know that for the given problem I have to do X representation with kernel regression, or for another problem I have to do Y representation with say neural network? I mean, do you think this is a built knowledge at the moment, or is something we're developing?
So I don't think there is a formal complete formal understanding. Now, of course, this is a problem on which people who do who study machine learning formally are working a lot. There is a lot of work on the phase diagram of the parameter space of neural networks. So there is a lot of very interesting work going on getting a deep understanding of all of these machine learning techniques. My personal understanding, my personal wisdom would be that you always have a data complexity trade-off. So if you have very little data, then the best thing you can do is probably a representation that is very low dimensional, like a pair representation, and do a linear regression on it. If you have an intermediate amount of data, then I think that going up in body order and using kernel ridge regression is probably what is going to. And empirically, there have been several attempts at using deep learning on standard molecular data sets, and I still haven't seen one case in which they beat a kernel regression method if the comparison is fair. Okay, so my impression is that we are still far, and we might never get, because in the end, you want couple cluster and QMC accuracy. So for the time being, reference calculations are going to be expensive. So I think that at the moment, either kernel ridge regression or a very simple naive neural network are the way I would go. But you have people who think otherwise and would go, for convolutional neural network.
Yeah, I think.
So I see there is a question. Sorry.
Yeah, no, sorry. Yeah, so there's a question. Maybe actually, yes, there's a question from Michelangelo, who's a student in my group, and he's asking, can you give a quick insight on how to construct a tensorial covariant representation?
Let me see if I have some backup. No, I don't have backup slides because stupidly I truncated these. Wait a second. I just go back to the. Okay, so how you build a tensorial representation. So essentially the idea is that okay, so this is actually just look at this. This esoteric looking object, okay, is indicating a tensorial feature. So what you see here is that you have the bra side of the Dirac notation contains coordinates that are actually associated with the position of the atoms. So you need to describe the position of your atoms, but on the right-hand side, you have this lambda mu that instead refer to the property that you're trying to predict. So the idea is that you need both a basis to describe your structure and a basis to describe your property. Okay? And when you combine the two, you basically need to keep the basis that describes the property is fixed in space. The basis that describes the structure is averaged over. I understand that this is not a complete answer, but this is not really something that I can explain without a blackboard and a lot of chalk.
Yeah. Okay, so I guess we're more or less running out of time. So I guess I would like to thank you again, Michele, and all of you who have watched this. So we have a number of viewers fluctuating between 40 and 50 at any given time, which I think is pretty good. I do apologize for those of you who are watching this at weird time in the morning or weird time in the evening, but we can accommodate any time zone. So I hope to see everybody, even virtually, at the next seminar next week. Thanks a lot.
Thank you, everyone. Bye-bye.
Bye-bye.